All right, guys, in this video, we are going to do some more modeling with logarithms. This is going to be our last video for the logarithm section. It kind of ties up unit 3 or chapter 3. And so this is the rest of section 3.7. In the first video, we talked about solving equations, but in this one, we're talking more with like actual modeling. We're going to use some of those skills in this. All right, so first thing you're seeing on your screen there is a little property about logarithms. If you were to show logarithms with a modeling thing, maybe in a table, it says for any given data, if the input values change proportionally over equal length output values, then the logarithmic model is appropriate. It's kind of backwards from exponentials. So exponentials, you would have seen that the x value changed at a constant rate, whereas the y value changed by either multiplying or dividing by something every time. This time those are switching. So the y's are going to stay constant, whereas your x's are going to change proportionally. So you would multiply by something every time or divide by something every time. So just if you ever get a model and they say, is it logarithmic? You can tell by just checking for that proportionality on the on those inputs. Okay, so let's get into an example here. Our example says that we've got a function, L of x is equal to a plus b natural log of x. Find the values of a and b, and they've given us a little table here. So we're going to use that table to our advantage. Although we don't know a and b, we can end up writing some equations to help us find them. So that's what we're going to do. We're going to use that generic form they gave us in the problem, and we're going to use that to help us find what the a and b values are. That way we could write an equation that models that a little bit better. All right, so here we go. So I'm going to use this equation that we see up here, but what I want you to remember is that when you see L of x, that stands for a y, right? So what we're going to do is we're going to plug our x and y from one point into this thing and set up an equation there, but then we'll do the exact same thing with the other point. So I'm going to have one of these here where we're going to talk about L of x. Remember, that's y, so I'm going to replace that with a 3. We're going to say that is equal to a plus b natural log of, and at that point, my x value was 2. So natural log of 2. That is one equation that we can use. We also have another equation where if we use the other point, the 5, 7. So in that one, the y value was 7. That's equal to a plus b natural log of the x value, 5. So we've got two little equations here that we can use to help us solve. And what we can do is we can write a system of equations. Okay, so I'm going to put that here. Use a system. Now, substitution would be a little bit trickier to use on this one. That seems to be what we typically go for. But I'm thinking we could actually probably have some luck with using elimination as a method. So let's stack these. We've got 3 equals a plus b natural log of 2. We also have 7 equals a plus b natural log of 5. And what I want you to notice is you see how they both have an a term like this. If I were to subtract one of these from the other, let's say I subtract this one from the one above. If I do that, then I will end up being able to get rid of my a, because that's going to make this negative, and this over here. All right, so this would be 3 minus 7, which is a negative 4. A minus b, which is nothing, right? I'll write that for now. And then over here, b natural log of 2, right? We have this b natural log of 2, and we're subtracting b natural log of 5. And no, those can't combine, but at least we're getting closer to where we could be. Right? I'm also not a huge fan of this negative here, so I'm thinking we could potentially just distribute through a negative, and that way we don't have quite as many. So or you can leave it. It doesn't really matter either way. But I think I might get rid of it just to make things a little bit easier on us. I don't know. We'll leave it for now. It's fine. All right, we're going to leave that for now. And then I'm going to look at this equation right here. You see how both these natural logs have a b in it? I'm going to factor a b out. That makes natural log of 2 minus natural log of 5. All right, now we can divide by the natural log of 2 minus the natural log of 5. So this would be a negative 4 over natural log of 2 minus natural log of 5. And that should be equal to your b value. We can type that in a calculator. I need to grab one sec. And then we'll get a value here. So if you go in your calculator, I need to turn my brightness down as per usual. Okay. And then you're just going to type in what you see. So negative 4 divided by your natural log of 2 minus your natural log of 5. Right? It comes out with your answer, and that says about 4. So my B is about 4.3654. Now, we're not done because all I have here is the B value, and it said to find both A and B, right? But this is one of my values. So I'm going to point that out. And then we're going to take this to help me find the other one. So now we're going to pick one of these equations. It doesn't matter which one. I'm just going to go with the first one because that seems simple. And we're going to plug this guy in. So I'm going to take that 3 equals A plus B natural log of 2. And I'm going to plug this B value in. 3 equals A plus, and then this was 4.36, let's say about 365. Right? Now, when you solve this, I need to subtract this guy from 3. So we're going to subtract this guy, subtract 4.365 natural log of 2 from that 3. Okay, it goes away here. And on this side, when you subtract 3 minus 4.365-ish natural log of 2, we end up with about negative 0.0258-ish for your A value. So really, let's say that we could round it to 3 decimals, but this will be fine. Okay. So we got the A and we got the B. All done. All right, we got one more problem here. And we are going to write this out. So I'm gonna suggest that you pause the video so you can write this out and then come back when you're ready to go over it. All right, so we've got a question here talking about sound. It's measured in decibels, and the intensity level we can say is in decimals, and it has a intensity I in watts per meters squared. That's going to be modeled by that equation that you see, and we're given some information here. It says a sound of noisy traffic intensity has an intensity of 1 times 10 to the negative 5 watts per meter squared with 70 decibels, right? And a loud concert has an intensity of 1 with 120 decibels. We're going to write an equation for B of I, and then we're going to talk about where eardrums can burst. But we're going to first start with that part A question, write an equation, and then we'll be able to use that to help us. All right, so similar to what we did on the last one, we're going to write out a couple different equations with the information they gave us. So they've given us basically coordinates. I know that doesn't feel like it, but they did. The values that they gave us here, when they gave us that intensity, that right there was 1 times 10 to the negative 5 as your X value. And then the Y value that went with it was 70. And we have another coordinate with the other values, they said has an intensity of 1, so that's your x value, and then the y value is 120. So right there, you're given x's and y's, and we're going to do the exact same thing we did on the last question, where we're going to set up some equations and then solve a system. So for this first one, the equation I'm going to use is I'm going to plug everything in up here. So remember, b of I is your y value, so we're going to say 70, and that is equal to a plus b log of that x value, or I in this case, 1 times 10 to the negative fifth. All right, we have another equation by plugging in the other values. So we're going to plug in the 120 for the y value, or that b of I. And then the other part, we're going to plug in 1, where that would go. All right. So now we need to set up a system here. And since they're already kind of stacked, might as well go ahead and just use that. I'm going to do the same thing we did before and use that elimination method. So we're going to subtract these two. And so you'll see here, when we do 70 minus 120, I get negative 50. A minus A is gone. Here we have our B log of 1 times 10 to the negative 5 minus B times log of 1. Now, some of you guys may have already recognized the fact that we can calculate log of 1. Anytime you have log of 1, the answer is 0. So I'm going to clean this up a little bit. We're going to get rid of unnecessary things. Because here, if I have log of 0, right, really this is just b times 0. And so that just goes away. We don't need to even write it. All right, next thing, we are going to continue solving this. If you plug in log of 1 times 10 to the negative fifth, let's see what we get there. So that way we get maybe a value. I'm always really slow with my calculator. But when I did log of 10 to the negative fifth, I don't know if you can see, the answer was actually negative 5, which makes this even better. We get b times a negative 5. And so there, I can divide both sides by that negative 5. Okay. And then here, this gives me 10 for my b value. So it actually comes out to be a really nice number. All right, we're going to do the thing where we take this and plug it into one of those equations to get a. I'm just going to use, I think, it doesn't really matter, but I think the bottom equation is easier because we have that log of 1. So I'm going to go with that one. The 120 equals a, which we don't know, plus we just got b was 10, 10 to the log of 1. Okay, but we remember that log of 1 is simply just 0. So this makes 0. A is 120. So when they said to write that equation out, we're going to write that equation over here, b of I, my bad. B of I equals, and we'll have the A value, which was 120, plus, and then we want log of, B log of I. So B was 10, log, I'm running into like the shiny part of my paper over here, log of I. I don't know if you can see that very well. Let me rewrite it. My bad. I started too far to the right. Log of I. That's better. All right, that's our equation. All right, so on our next part, we need to use this equation. So that was my official answer to the question for part A. But we want to look at my part B, where they said human eardrums, they burst at a certain decimal, right? They said at an intensity of 1 times 10 to the fourth. So watts, they're giving me that. We're supposed to figure out how many decibels are required to burst that eardrum. So we have a little bit of work to do with our equation that we just made. So I'm going to keep that handy and I'm going to refer back to it. Okay. So this is the equation that we had. And we're going to plug things into it. All right, so they said we're using an intensity of 1 times 10 to the fourth. So I'm going to use that in my equation. B of, and we're going to use 1 times 10 to the fourth. That's what we're plugging in. And then, so it's just going to look like 120 plus log, 10 times the log. Here, we'll do that. 10 log of the 1 times 10 to the fourth. All right, so there we have our problem where we can just work this out. We got 120 plus, and then we can rewrite this log of 10 to the fourth. Remember that this is a log base 10 of 10 to the fourth. Really, this is just 4 as the exponent. So we have this 10 in front times that 4 from that exponent. 120 plus 40. And that gives us an answer of 160. And that was decibels. All right. So that was part B, whereas the other one was part A. All right, guys, that is it for this lesson. I hope all of that was clearish. And we'll see you in the next one. Bye.